Welcome. Today I will be discussing the fourth order Butterworth bandpass filter, which uses two UA 741 CN op amps. In this configuration, you have two second order op amps, which combined make a fourth order Butterworth bandpass filter. By inputting these frequencies in these ranges here, you can look at the entire characteristics of the attenuation and the gain, which will be unity gain around 3.16 kilohertz. To showcase this, I will put in 700 hertz and run that. And you see that this is in the lower reject band, so it's starting to reject it, but not quite. And if you go a lot lower, say you go into the 300 right here, you're going to definitely see that it's getting rejected then. So we'll do 300, run that, and you see that it's now rejecting that frequency. And we're going to go to 3.16 kilohertz, and we're going to see that is going to be in unity. See, it's in unity, so it's having maximum gain or unity of 1, which means it's passing that. And we're going to go which is calculated right here. And we're going to go, let's put in 20 kilohertz. And you're going to see that is starting to be suppressed quite a lot. And if you really go crazy and you put in 50 kilohertz, then it completely locks it. As you can see, it's completely blocked, just like on the other side of the frequency band. So as you can see in this, the reason I did this was so I could look at the non-linear elements. If there are anything present, I could look at them. One of the things I considered was the skew rate, which means that as the frequency of our signal increases, and if you have a larger amplitude, it takes longer for the op amps to be able to go and cycle through that frequency amplitude. And as the frequency goes up, it's harder there's strain on it, so it cannot keep up with it. And that's what causes it to not be able to operate correctly. And it messes up your what you're trying to actually do. And you can actually see it in plots and stuff. There's another circuit I built, which was one that I like using, which is this one here. This circuit I use for inputting. I basically use I basically inject frequencies in here using this from these ranges here. Well, you can do whatever you want because it goes through a huge range and you just specify it. But this sort of acts like a pseudo frequency generator, and it just cycles through a bunch of frequencies so you can get it done quickly without having to input them individually. And then what I do when I do this is it allows me to be able to speed up the analysis of the circuit. So when I'm troubleshooting, it helps a lot, and it also saves you a ton of time. I went ahead and saved a bunch of stuff because I had problems with sometimes this not working because it just glitches out because I got a lot of stuff running. So I've saved some stuff in a document here that I can go over, so you can just see it directly without having to go and pause and make sure you got the right timing and everything else. And what I have here, as you can see, this is the Bode diagram, and if you look in the middle here, this upper line right in the middle here, this is the mid pass band, and this is where this is our goal. Our goal was to get a band pass between 1 kilohertz and 10 kilohertz, which is what we have, a -3 decibel drop, or you can take the your mid band and frequency, I mean your magnitude, and you multiply that by 0.707, and it'll give you these 2 points, which is your upper and lower um, cutoff frequencies. That's how you can test to see if you are if your circuit is working properly. This little blip right here is caused, like I was talking about, that skew rate. This is where the frequency gets so quickly that it starts sending back some of the when it, some of the output back into the input, and that's what causes it to actually have gain in this area because it's not non-ideal. So that's what this is. I had to study a little bit and try to figure out what that was, and I spent almost a day trying to figure out how to get rid of this. But it's actually just inherent in specifically the 741 op amps. They have this problem, and I think other op amps also do, because it's just, and I try to model it. So my models try to I try to characterize and add in as much information I can so that I model as much real world behavior, even though it's a simulation. So then, as I was telling you before, this right here lets you go over all the different various uh, frequencies. The input frequency is in blue, and the output is in orange. And I went through specific key bands and looked at each of them so that you could see there's a attenuation here and gain right here of 1. So we got that. And then you can see it one way here in a bode plot or diagram, and you can see it in these individually progressing through the frequencies individually. And there's a little bit comment here that explains what's happening at each frequency. And if you zoom in on this document, or you can get a little bit more information about the peak to peak and maximum values for V out. And I noted here on this one that gain is 1 and the input and output are in phase. And that's a characteristic of the mid band of a bandpass filter. And I also noticed that that in a bandpass filter, the input leads the output below the pass band due to the high pass phase shift, while above the pass band, the output leads the input due to low pass phase shift. That's something that's kind of interesting. I was trying to figure out why there was a phase difference, and that's the reason why. So as you can see, I went through all these. The reason it says corrected is that my original design was off because I mixed up a few decimal places, just a single decimal place, and threw everything off. And I had a smudge mark or something on my paper, and I messed up on a resistor value, which a single number can mess up an entire filter or anything in a circuit. So that's the reason why it's good to have all these tools to check your work until you can find where you made your mistake. And also it's good important to make mistakes so you can go and know if something's wrong, where you can trace your steps back to those from those mistakes and find where you went wrong. And it really helps. So every time you make mistakes, I look at it as a learning exercise rather than a failure, because every time I make mistakes, I get better at doing the stuff anyway. So yes, this is where the information I have here. There's some stuff I wanted to discuss also, because I'm not really good at these videos, but these plots show us how the circuit responds to different frequencies, as I was saying. And the vertical axis represents the gain, of course. And that tells us how much the circuit amplifies or reduces the signal at each frequency. So you can look at this on all these graphs and to tell that. Whenever the gain is above 0 decibels, which is right here, the circuit is amplifying the signal. meaning the output is larger than the input, meaning that the output is larger than the input. So that's why it's important to color code these and not just use the same color, because then you might not know which one of these is the input or output. Here in the pass band, which is going to be, this is the pass band here. You can see that the gain stays close to our measured value, or mid, which is going to be the point at the top here. It stays close to this value right here. And which means the circuit is letting those frequencies through with minimal loss. That's what this is. So the higher, higher the slope is on both sides, that means that it's letting it through with minimum loss. So it's a really good thing to have if you don't want to have distortion and you're trying to take in specific frequencies. It's really good to use a fourth order or even an eighth order if you're really ambitious. This peak shows us the frequency where the circuit provides the most amplification as well. In the center of the band, the gain reaches its maximum. So that's the point right here. And it's the resonant region where the filter is designed to operate. Now we're going to look at the lower side of this and the upper frequency sides of this. Here's where the attenuation occurs, here and here. And below this frequency, here and here, the gain drops below 0 decibels. Which means the circuit is attenuating the signal, reducing its magnitude. So it's reducing its magnitude. It's reducing it the whole time, but after it gets out of the range here, it drastically drops. In the stop bands, the gain drops sharply. So our stop bands will be right here, our lower stop band, and our upper stop band, which was actually here and here. And that's where it drops drastically on both sides. That's the filter rejecting frequencies. That is the filter rejecting the frequencies that we don't want on both sides. The slope here shows how quickly the filter attenuates unwanted frequencies. So the greater the slope, the greater the attenuation. And this attenuation is intentional because it ensures us that the frequencies outside the pass band, right here, are significantly reduced so they don't interfere with the desired signal. That's a very important thing. So if you don't have a lot of noise or other signals and stuff, it lets you lock down on exactly the frequency that you want. Some other information that from doing a bunch of research on this, I noticed that the measured gain doesn't perfectly match the theoretical curve. And this is common in all design. That's expected because real components have tolerances like 5, 10% resistors. Even capacitors have actually inherent ranges. In fact, every component does. So that's important to know. And small mismatches cause slight shifts in the gain profile. A single mistake can set you back an entire day or make an entire circuit not work when you're dealing with frequencies and trying to go and pass them or attenuate them. So it's important to not get discouraged because it does take hours sometimes, especially when you're learning this stuff. So anyway, even with those variations, the overall shape, amplification in the passband, and clear attenuation outside of it are usually enough so that you can tell that your device is working, and then you can fine tune it. The first time I did this design, and I went through the whole process, simulation, building the circuit, everything, the research, it was completely far off. But as you work, you have to sometimes rework it several times, and it helps you work out the bugs, and just like programming. Um, so the overall plot shows us exactly what we expect: strong game in the passband and clear attenuation outside of it. And the gain curve confirms that the filter behaves as designed, passing the targeted frequencies and attenuating everything else. And now that we've looked at the raw gain measurements, let's switch back to the Bode plot and talk a little bit about that before concluding this simulation explanation of our project. This will give us a clear frequency domain view of how the circuit behaves. So the Bode magnitude plot shows how the gain changes as frequency increases. And higher points mean more amplification, as we said before. I know we're repeating stuff, but I'm trying to make sure that I cover everything. The lower points, of course, mean attenuation, the same thing that was going down here. The attenuation is occurring here. Attenuation, I mean, gain is occurring here. Unity, and as it drops away from the pass band, and then it's attenuated again. Same thing here, like before. So that has all been covered. Okay, so what else do we need to cover? Okay, so here's one other thing that I found interesting. On the left side at low frequency, the gain drops sharply. This is called the lower frequency attenuation region. And of course, this one is called on the right side is called the high frequency attenuation region. So simple terms, but going over the key points of the graph. So anyway, these two slopes are what define the stop bands I was talking about a minute ago. So the lower and upper attenuation regions define the stop bands. And that in turn determines the frequency the filter rejects. Now let's mention what roll-off slopes are, because this is something that I did not understand, but after reading a bunch, I also noticed that with a fourth order bandpass filter, we have about a negative 80 decibel per decade outside the pass band of roll-off. At this point, I don't know a lot about that, but I'm sure I'll learn more about that. But that's just something that's characteristic of this specific circuit. Um, even though the exact gain values differ slightly from the ideal model, the overall shape, the pass band peak, and attenuation on both sides matches the expected behavior of the fourth order bandpass filter. So once again, all this is basically telling us that the circuit is performing as designed. At least the simulation is. The simulation is working as designed. So that concludes everything. I think I've repeated myself several times, but we definitely have covered everything that we did in Simulink and the functionality of our circuit. Hope you enjoyed. It's probably terrible, but I'm not really good at recording myself or videos and stuff. But it was, I hope you learned something and enjoyed. All right. Bye-bye. Turn this off.